How can identifying the electrophile, nucleophile, and leaving group help you to figure out how a reaction will progress, no matter the reaction? And how can the similarities and differences across reactions also help you to predict how molecules will interact with each other? I'm Amanda Swearingen, and these are a couple of questions that we're going to explore in this lesson on nucleophilic acyl substitution. Specifically, we'll explore a reaction mechanism common for carboxylic acid derivatives. First, by characterizing the similarities and differences between the derivatives, as well as the two major steps involved in the nucleophilic acyl substitution. Then, we'll focus on how the variations of the same mechanism progress by comparing and contrasting three reactions: transesterification, amide formation, and hydrolysis. Before we tackle this lesson, take about a minute to read and familiarize yourself with the question stem. The question presented is pretty straightforward. Figure out what results when the same starting material, methyl pivolate, interacts with three different molecules. In your organic chemistry class, you might have tackled each reaction individually using memorized mechanisms, but you're prepping for a huge amount of material for the MCAT. So let's see how you can be more strategic to answer this question. First, we'll focus on the similarities between the three reactions to predict how the molecules will interact with each other during these reactions. Then, we'll see how the differences between the reactants and conditions will help you to anticipate the final result for each reaction. Recall from the question stem that while each of the products of our three reactions will be different from one another, they all have something in common. They're all carboxylic acid derivatives. So let's review how we can recognize when a molecule is a derivative of a carboxylic acid in the first place. And that has to do with this structure here, a double bonded oxygen to an alkyl group, known as an acyl group. On the other side of the acyl group is the substituent that distinguishes the derivatives from each other and determines the overall functional group. Since we were looking at derivatives of carboxylic acids, let's start there. Starting with the common structure of the acyl group, the overall functional group is further defined as a carboxylic acid when it's attached to an OH or hydroxy group. Each carboxylic acid derivative is defined by what substituent replaces that OH group. So what substituents define each of the following derivatives as either an ester, amide, or an acyl halide? When an acyl group is attached to an OR group, we have an ester. If we replace the OH group with an amine, we have an amide. Finally, when the OH group is replaced with a halogen, such as a chlorine, we have an acyl halide. While it's certainly important to distinguish molecules from each other for accuracy in naming the correct products, efficiency getting to the products is made possible by also zeroing in on similarities, particularly how similar structures confer similar reactivity. That's what the first prompt gets at, how the carbonyl structure dictates similar functionality when interacting with other molecules. The electronegative carbonyl oxygen is extremely electron withdrawing, creating a strong dipole by pulling electron density away from the carbonyl carbon. Go ahead and make a prediction for what function carboxylic acid derivatives will have in common during a reaction due to the carbonyl structure. Because of the strong dipole created by the oxygen, the carbonyl carbon is partially positive. Further, because it is double bonded to oxygen in the first place, the carbonyl carbon is sp2 hybridized, giving it planar geometry, thereby making it really susceptible to nucleophilic attack, and so we can expect that carboxylic acid derivatives will act as an electrophile during reactions. Now that we've determined why we should expect carboxylic acids and their derivatives to act as electrophiles, we can see the immediate pertinence for this deduction for each of our reactions. Our starting material, methyl pivolate, is itself a carboxylic acid derivative. The methoxide is an OR group, which we know means it's an ester. As an electrophile, we also know that methyl pivolate is susceptible to nucleophilic attack, which leads us to the next step we should take when working with any reaction: identify the nucleophile. Just as the partial positive charge on the carbonyl carbon helped us to identify its electrophilic nature, we can use the opposite situation to find the nucleophile. Because the ethanol solvent is essentially an aqueous solution, we can expect that the salts will dissociate, leaving us with a negatively charged ethoxide as our nucleophile. And that connects directly to the first step in the nucleophilic acyl substitution mechanism, nucleophilic attack. The nucleophile adds a fifth bond to carbon, which it really doesn't want. Here's where the magic of the carbonyl structure really comes into play, providing the built-in solution to our 5-bonded carbon problem by allowing the electrons to kick up to the electronegative oxygen, and this will then leave us with our tetrahedral intermediate. So looking at its structure, why can't the tetrahedral alkoxide intermediate be the product of this reaction? Just like our nucleophile, the intermediate here is an alkoxide, so we can expect that it too will act like a nucleophile. The difference here is it doesn't have an electrophile to attack, but because it's negatively charged, it's still too reactive to remain in its present form. Instead, the negative charge can be stabilized by spreading out the electron density through reforming the carbonyl structure. But nothing's changed. Carbon still doesn't want to make 5 bonds, and so it will force off the leaving group to regain that stability. How do we know that methoxide is the leaving group? Why not ethoxide? While this certainly does happen in solution, it's not very interesting because we'd be left with the same starting material. And this is the final step we should take when working with any substitution reaction. Identify the leaving group that will yield a new product. In this case, a new OR group, making it a different ester, hence the reaction name, transesterification. Given the setup, how can you tell that this reaction will proceed in a similar way to the previous transesterification reaction? As before, the first step is to identify the electrophile, and this is made easier because we have the same starting material, which we again expect to act as the electrophile. The second step is we need to identify our nucleophile. Well, it's not exactly the same. It does have a very similar structure, as it too is a salt, this time with lithium instead of sodium, but it will dissociate in our solvent, leaving behind a nitrogen-containing anion. So we can predict the same first step in the reaction mechanism. We'll have our nucleophilic attack on the carbonyl carbon, leading to a similar alkoxide intermediate. With the same type of unstable reactive intermediate under extremely similar reaction conditions, we can further predict that to regain that stability, our carbonyl group will reform and force off the same methoxide leaving group. So as we can see, the only real difference in this reaction is the identity of the nucleophile as an anionic amine, creating an amide. The last reaction, hydrolysis, may initially look very different, but we'll see that the same underlying features are still present, just with an extra layer added. Again, our first step, identifying the electrophile, no sweat, as we still expect the methylpivalate to act as the electrophile. While we certainly have an aqueous solution with water as the solvent, the missing piece is that the resulting nucleophilic anion is nowhere to be found. The mystery of the missing nucleophile can be solved by focusing on the different reaction conditions we have. The first two reactions occurred in basic conditions, but this reaction takes place under acidic conditions, meaning that water is going to act as a base, making it both the solvent and the nucleophile. Unlike the previous reactions, water isn't a good nucleophile, and so it needs a catalyst before it can attack that carbonyl carbon. So although water does act like a base under acidic conditions, it's a weak base, and so it's too weak to attack, as it's very stable and not very reactive. Again, the structure of the carbonyl group provides us with a built-in solution. In the presence of acid, the carbonyl oxygen will be protonated because of its high electron density. How does protonating the carbonyl oxygen facilitate water to attack the carbonyl carbon? So as we know, the strong dipole we already had made the carbonyl carbon electrophilic. But after protonation, the positive charge on the resulting oxonium pulls even more electron density away, essentially stripping any negative charges away from the carbon, making it even more electrophilic. Such a strong electrophile can then be attacked by even weak nucleophiles, like water. Just as before, we'll need to kick up the electrons to the oxygen to avoid a 5-bonded carbon, leaving us once again with a tetrahedral intermediate. We know what's coming next, the second step of our mechanism, reform the carbonyl and kick off the leaving group. But let's not get too hasty. As we saw in the transesterification reaction, we want methoxide to act as the leaving group in order to form a new product. But it isn't the only leaving group in solution. This time, the alternative leaving group water poses an even bigger problem. Given the structure of the intermediate in the hydrolysis reaction, why is water actually a better leaving group than methoxide? Because the water group is positively charged, it is more reactive and unstable. This stability could easily be restored by leaving and reforming the original starting materials. On the other hand, if methoxide leaves, it is a negatively charged reactive ion that is not stabilized under acidic conditions as it was previously in the basic salt-forming conditions. Therefore, in order to drive the desired reaction forward, the proximity between these two potential leaving groups allows for a reaction hack, if you will, in the form of proton transfer. Given the positive charge on the oxygen of water, it can easily be deprotonated, transferring the proton over to methoxide. Now methoxide will be a much more stable leaving group when it was forced off to reform the carbon-oxygen double bond. While this was the final step in the earlier reactions under basic conditions, because we required an acid catalyst for the hydrolysis reaction, the final step added to our nucleophilic acyl substitution mechanism is to regenerate that catalyst, leaving us with an OH group, making the product here a carboxylic acid. As we just saw, hydrolysis is still a nucleophilic acyl substitution reaction, but each step of the mechanism requires some help due to the reaction conditions. In this lesson, you saw a lot more than just 3 reactions that undergo the same nucleophilic acyl substitution mechanism. You also saw predictable ways that molecules will interact with each other during a reaction in order to form the most stable product in the end. So, by identifying the nucleophile, electrophile, and leaving group, you can anticipate how any reaction will progress. Now that you have a deeper understanding of the predictable ways molecules will interact with each other during reactions, I hope you apply the same strategy to other mechanisms beyond nucleophilic acyl substitution, not only to increase your success on the MCAT, but also your efficiency preparing for the MCAT.